Welcome! Today, we'll tackle an exciting problem from LeetCode, problem number 1079, letter tile possibilities. This problem challenges us to explore all possible permutations of given tiles with unique constraints. Stay tuned as we break down the problem and solve it step by step. Imagine you have a set of tiles, and each tile has a letter printed on it. The challenge is to figure out how many different sequences of letters you can form using these tiles. The important thing to note here is that each tile can be used exactly once in any given sequence. So, for example, if you have 3 tiles, you can rearrange them to create different sequences, but you can't reuse any tile more than once in a single sequence. The goal is to calculate the total number of possible non-empty sequences that can be made. For input, we receive a string called tiles, which represents the tiles we have. It consists only of uppercase English letters, and the length of this string can range from 1 to 7. The output is a single integer, representing the total number of unique sequences we can form from these tiles. Let's look at an example to understand this better. Suppose the input tiles is equal to AAB. From these tiles, we can create sequences of different lengths. For single-letter sequences, we have A and B. For 2-letter sequences, we can form AA, AB, and BA. For 3-letter sequences, we can get AAB, ABA, and BAA. When we count all of these unique sequences together, we get a total of 8. Now, take another example where the input tiles is AABBC. Here, we have 6 tiles, and the total number of unique sequences is 188. This count includes all valid combinations of lengths ranging from 1 to 6. It also accounts for the repetition of letters, ensuring that no sequence is overcounted. This example demonstrates how the problem scales as the number of tiles and the repetitions increase. Now consider the input tiles as XYZ. Here, all the tiles are unique, so there are no repetitions to manage. For single-letter sequences, we have X, Y, and Z. For 2-letter sequences, we can form XY, XZ, YX, YZ, ZX, and ZY. For 3-letter sequences, we can create XYZ, XZY, YXZ, YZX, ZXY, and ZYX. When we add these together, we find there are 15 unique sequences in total. The constraints for this problem ensure that the length of tiles is always between 1 and 7, and the string will only include uppercase English letters. Some edge cases to consider include inputs like AAA, where all tiles are identical, meaning the total sequences are limited by the repetitions. Another case is when all the tiles are unique, like ABCDFG, which maximizes the number of permutations. For the smallest input size, such as A, the output will simply be 1, as there's only one sequence possible. Finally, mixed repetitions, like AAB, require careful handling to avoid overcounting duplicate sequences. To tackle this problem, we started by considering 2 main approaches, the brute force approach and an optimized backtracking approach. The brute force method is intuitive. You generate all possible permutations of the tiles, including those of different lengths, and then count the unique ones. This involves recursively exploring every possible sequence while keeping track of what tiles have been used. However, the downside is that this approach is computationally expensive. Not only does it generate all permutations, but it also requires extra memory to filter out duplicates, which makes it inefficient for larger inputs. Now, the optimized backtracking approach improves upon this by leveraging the frequency of each tile to avoid generating duplicates in the first place. Instead of generating all permutations and filtering afterward, we systematically explore sequences while ensuring that no tile is used more times than it appears in the input. This is done using a frequency counter, such as Python's collections counter, to dynamically update the available tiles during the recursive process. This strategy significantly reduces redundant calculations and memory usage. Here's how the optimized backtracking approach works step by step. First, we initialize a frequency counter to keep track of how many tiles are available for use. Then, we recursively build sequences by choosing a tile, decrementing its frequency, and exploring further combinations. Once we complete the exploration for a specific tile, we restore its frequency, which allows us to try other combinations. This backtracking ensures that we systematically explore all valid sequences without exceeding the frequency constraints of any tile. Importantly, every non-empty sequence we generate during this recursive process is counted toward the total. The implementation of this approach is both elegant and efficient. As shown in the code snippet, the backtrack function iterates through the counter, checking if a tile is available to use. If it is, we choose the tile, decrement its count, and make a recursive call to explore further sequences. After finishing with that tile, we backtrack by restoring the count, allowing for other sequences to be formed. Finally, the total number of sequences is returned as the result. Now let's compare the two approaches to understand the trade-offs. First, brute force generates all permutations and filters out duplicates afterward, which leads to unnecessary computations and higher memory usage. In contrast, backtracking avoids duplicates during the exploration itself, making it far more efficient. When analyzing time complexity, brute force requires O(n) for generating permutations, plus additional time to filter duplicates. On the other hand, backtracking operates on a complexity of O(k) to the power of n, where k is the number of unique tiles and n is the total number of tiles. For space complexity, both approaches require O(n) space for the recursion stack, but brute force incurs additional memory overhead for storing unique sequences, which backtracking avoids. Ultimately, backtracking is the optimal choice because it directly addresses the problem's constraints by ensuring that no tile is used more than its frequency. This eliminates unnecessary work, making it both time efficient and space efficient. Additionally, the clarity of the implementation, with the dynamic adjustment of the frequency counter, makes it an elegant and robust solution to the problem. To approach this problem, we start by defining the challenge. We need to calculate the number of unique sequences that can be formed using the given set of tiles, which may include repeated characters. For example, with tiles like AAB, we need to consider all possible combinations of different lengths, while also accounting for duplicate letters. This is where the constraints play a crucial role. The tiles can be used in any order and the sequences can range from a single character up to the total number of tiles available. To solve this, we employ a backtracking algorithm. Backtracking allows us to explore all possible sequences systematically. The key idea is simple. For each tile, we have two choices, either included in the current sequence or skip it, ensuring that every possible permutation is considered. To manage the repeated characters effectively, we use a frequency map. This map keeps track of how many times each tile is available for use. For example, given AAB, the frequency map starts as A2, B1. This way, we avoid invalid permutations, such as using a 3 times when it only appears twice in the input. The backtracking function lies at the heart of this approach. It is a recursive function that builds the sequences step by step. First, we define the base case. If there are no tiles left to use, the recursion stops. For the recursive case, we iterate over all available tiles. If a tile is still available, meaning its frequency is greater than 0, we include it in the current sequence, decrement its frequency, and then make a recursive call to continue building the sequence. Once we finish exploring this branch, we backtrack by removing the tile from the sequence and restoring its frequency in the map. This ensures that other branches remain unaffected. Additionally, to ensure we only store unique sequences, we make use of a set. Since sets automatically handle duplicates, we don't need to perform extra checks. Finally, the function is designed to generate sequences of all possible lengths, from 1 up to the total number of tiles. This ensures we capture every valid combination. To produce the final output, we simply return the size of the set containing all unique sequences. This value represents the total number of distinct sequences that can be formed. There are several key insights to highlight here. First, the use of the frequency map ensures that we avoid duplicates during sequence generation. For instance, with AAB, we would never generate an invalid sequence like AAB because the frequency of it is capped at 2. Second, this approach is efficient because it eliminates the need to generate all permutations first and then filter out duplicates. By ensuring uniqueness during the generation process itself, we save significant computational effort. Finally, backtracking is an ideal strategy for this kind of problem. It allows us to systematically explore all valid sequences by making decisions at each step, whether to include or exclude a tile, while efficiently navigating the problem space. Let's take a closer look at the data structures that make this algorithm work efficiently. First, the frequency map is essential. It tracks the available tiles and their counts, for example, a 2, B, 1, for the input AAB. This data structure prevents the creation of invalid sequences and allows us to efficiently update tile availability during recursion. Second, the set is used to store unique sequences as they are generated. This is a simple yet powerful choice because sets automatically handle duplicate entries, which simplifies the logic of the algorithm. Lastly, the recursion stack plays a critical role. Since backtracking uses a recursive function, the stack is implicitly used to manage the sequence building process. Each recursive call represents a decision point in the exploration of the problem space, and the stack ensures we can backtrack to previous states without losing track of progress. Now let's focus on the key operations that drive this algorithm. First, the frequency map is updated dynamically during recursion. When a tile is added to the sequence, its count is decrement, and when we backtrack, the count is restored. This ensures that no side effects carry over to other branches of the recursion tree. Second, the use of a set to store sequences ensures that only unique combinations are retained. This eliminates the need for post-processing to remove duplicates. Finally, the iterative selection of tiles at each step guarantees that all possible combinations are explored systematically. By iterating over the tiles and deciding whether to include each one, the algorithm ensures comprehensive coverage of the solution space while maintaining efficiency. Let's wrap up by analyzing the complexity of this approach. In terms of time complexity, the worst-case scenario involves all tiles being unique, in which case we generate all permutations of the tiles. This results in a complexity of O(n). However, when the tiles include duplicates, the complexity is reduced since fewer unique permutations are generated. The exact complexity in such cases depends on the frequency distribution of the tiles. For space complexity, the frequency map and the set each require O(n) space, where n is the number of tiles. Additionally, the recursion stack requires O(n) space in the worst case, corresponding to the depth of the recursion tree. Overall, this algorithm balances efficiency and simplicity, making it an effective solution for the problem of generating unique sequences from letter tiles. This implementation solves the problem of counting unique sequences of tiles using permutations. First, we import the permutations function from the itertools module, which will help us generate all possible arrangements of the tiles. Inside the number tile possibilities method, we initialize an empty set called scene to store unique permutations. By iterating through lengths from 1 to the total number of tiles, we generate all possible permutations for each length using itertools.permutations. Each permutation is added to the scene set to ensure only unique sequences are counted. Finally, the length of the scene set is returned, representing the total number of unique sequences that can be formed. This approach is efficient because it avoids counting duplicate permutations by utilizing a set. Here, we begin by defining a method called numberTilePossibilities that takes a string tiles as input. The goal is to determine the number of unique sequences we can generate using the characters of this input string. To keep track of these unique sequences, we use a set string called scene, which ensures that all entries are distinct. Next, we convert the input string into a character array called tileArray to facilitate easier manipulation. We also create a Boolean array, used, to track which characters have already been used in the current sequence. Before starting the recursive process, we sort the tile array. Sorting is crucial because it allows us to handle duplicate characters systematically, ensuring that we skip over duplicates when necessary. We then call the backtrack method, passing in the character array, the used array, and empty string builder to build sequences dynamically, and the scene set. The backtrack function is where the recursive exploration happens, and we'll look at its logic in more detail next. Within the backtrack method, the first step is to check if the current sequence being built has any characters. If it does, we add it to the scene set, ensuring that only unique sequences are stored. Then, we iterate through the tiles array using a for loop. For each character, we first check whether it has already been used in the current sequence or if it is a duplicate of the previous character and the previous one hasn't been used. These conditions help us avoid redundant calculations and ensure that we only explore valid combinations. If the character passes these checks, we make a choice by marking it as used and appending it to the current sequence. With this updated state, we recursively call the backtrack method to explore further possibilities. Once the recursive call returns, we unchoose the character by marking it as unused and removing it from the current sequence. This backtracking process systematically generates all possible unique sequences, and the method ultimately returns the size of the scene set as the result. To understand how we calculate the number of unique permutations, let's consider the input tiles equals AAB. First, we initialize an empty set called scene, which will store all unique permutations we generate. Starting with the outer loop where I equals 1, we generate all permutations of length 1. For the given tiles, the permutations are a comma, and b comma. Notice that duplicates like a comma appear multiple times, but when we add them to the scene set, only unique values are stored. At the end of this step, scene contains a comma and b comma. Next, for I equals 2, we generate all permutations of length 2. The results include b, and some duplicates of these. After adding the unique combinations to scene, we now have a comma, b, and b. This incremental approach ensures we systematically account for all valid permutations while avoiding duplicates. For the next step, when I equals 3, we compute all permutations of length 3. These include b, and b, along with duplicates of these combinations. Once added to the scene set, we are left with unique permutations. At this point, scene contains all possible arrangements of tiles up to length 3, a comma, b, b, and b. The total number of unique permutations is found by taking the length of the scene set, which is 8. Finally, we return this value as the result. Now, let's analyze the input tiles equals ABC. We begin by initializing the scene set to store unique permutations. For permutations of length 1, we generate a comma, b, and c. These are all unique, so we add them to scene. At this stage, scene contains a comma, b, and c. Next, for permutations of length 2, the generated combinations are a b, c, b, c, and c, b. Adding these to the set gives us a total that now includes permutations of both lengths 1 and 2. The scene set at this step holds a comma, b, c, b, c, b, c, and c, b. Next, for permutations of length 3, we generate all possible unique arrangements of tiles. These include a b, c, b, c, b, c, b, and c, b. These are added to the scene set alongside the existing permutations of lengths 1 and 2. At the end of this process, scene contains every unique permutation of the tiles up to length 3. The total number of unique permutations is 15, which is the length of the scene set. This value is returned as the final result. Lastly, let's consider the input tiles equals AA. As before, the scene set is initialized as empty. For permutations of length 1, we generate a comma twice due to the duplicate letters, but only one instance is added to scene, resulting in a comma. For permutations of length 2, we generate a twice, but again, only one instance is added to the set. At this point, scene contains a comma and a. Since there are no additional lengths to consider, the total number of unique permutations is 2. This value is returned as the final output. To analyze the time complexity of this solution, we start by breaking it down into 3 main components. First, the outer loop iterates from 1 to the length of the input string, representing all possible substring lengths. For a string of length n, this results in n iterations. Next, for each substring length I, we generate all possible permutations using the itertools.permutations function. The number of permutations for a given length I is calculated as p n I, which is n factorial divided by n minus I factorial, or n slash ni. Finally, each generated permutation is added to a set, which ensures that duplicates are removed automatically. When we sum up all the permutations across all substring lengths, we get p n1 plus p n2, and so on, up to p n, which simplifies to n. Combining this with the outer loop and the set operations, the total time complexity becomes proportional to O, n asterisk n. The final time complexity of this solution is O, n asterisk n. Now, let's evaluate the space complexity. The primary contributor to space usage is the set scene, which stores all unique permutations of the tiles. In the worst case, where all tiles are distinct, the size of this set equals the total number of permutations, which is n. Therefore, the space required for the set is O, n. Additionally, we have the recursion stack used by itertools.permutations, where the maximum depth of recursion is equal to the length of the input string, n. This adds an O, n, space overhead for the recursion stack. When we combine these two components, the overall space complexity becomes O, n plus n. For large values of n, the factorial growth of n dominates, so the space complexity is effectively O, n. When comparing this approach to a brute force method, the differences in efficiency become clear. A naive brute force solution would involve generating all possible substrings, sorting each substring alphabetically to remove duplicates, and then calculating permutations. This process is computationally expensive because sorting adds unnecessary overhead, and duplicate substrings would still need to be eliminated. By contrast, the current approach takes advantage of itertools.permutations to directly compute permutations and uses a set to automatically filter out duplicates. This reduces redundant operations and ensures that both time and space are used more efficiently. The optimization comes from bypassing the need to generate and sort substrings manually, focusing instead on directly generating unique permutations. Now let's examine the best, average, and worst-case scenarios for the solution. In the best case, where all tiles are identical, such as quad A, there is only one unique permutation for each length. This simplifies the complexity to O, n, for both time and space. On the other hand, the worst case occurs when all tiles are distinct, like A, B, C, D, leading to the maximum number of unique permutations. In this scenario, the time complexity is O, n asterisk n, and the space complexity is O, n. For the average case, where tiles include a mix of duplicates and distinct characters, the complexity falls between the best and worst cases, though it tends to approach the worst case as n increases. To summarize, the factorial growth of permutations makes this solution efficient for smaller inputs, but it becomes computationally intensive as n grows larger, which is a trade-off inherent to problems involving permutations. One of the most common mistakes in solving this problem is not accounting for duplicate tiles. If the input contains duplicates and you don't handle them correctly, you could end up overcounting permutations. To avoid this, you can sort the input and use a visited array to ensure that the same tile isn't reused in the same position. Another frequent error is ignoring combinations of different lengths. Instead of generating permutations for only the full length of the tile set, you need to consider subsets of all possible lengths, from one tile to the total number of tiles. Inefficient brute force solutions are also a common pitfall. If you generate all permutations without checking for uniqueness as you go, you might waste a lot of time, especially on larger inputs. Using a set to store unique results or pruning duplicate branches early can make your solution far more efficient. A clear stop condition is also critical. If your recursion or backtracking doesn't have a well-defined stopping point, like when all tiles are used or the required length is achieved, you could enter infinite loops or get incorrect results. Finally, don't overlook edge cases. Inputs like an empty string, a single tile, or a set of identical tiles can expose flaws in your solution if you don't handle them properly. When tackling this problem in an interview, it's important to clarify constraints early. For example, ask if tiles can include non-alphabetic characters or if there's a maximum limit on the number of tiles. Knowing this helps you tailor your approach. Demonstrating optimization is another key interview skill. You might start with a brute force solution to show your understanding of the problem, then refine it using backtracking or even dynamic programming to highlight your problem-solving abilities. Be sure to communicate how your solution handles edge cases. For instance, explain what happens with duplicate tiles, empty input, or very large input sizes. Additionally, interviewers often expect you to discuss time and space complexity. Be ready to explain the trade-offs between different approaches. For example, backtracking with pruning is faster than brute force but may require extra memory for visited markers. Finally, It's worth noting that this problem is related to others like LeetCode 46, which involves generating permutations, LeetCode 47, which specifically handles duplicates, and even LeetCode 77 for combinations or LeetCode 784 for letter case permutations. A highly effective way to solve this problem is using backtracking. This approach is efficient because it generates permutations while handling duplicates and pruning unnecessary branches. Its complexity is typically n*n, but pruning can reduce this significantly. Another potential method is dynamic programming, where you count permutations based on state transitions. However, this is less common in interviews and is more suited to specific variations of the problem. If you prefer not to use recursion, iterative generation with stacks is an option. This method can be more memory efficient, but it's often harder to implement and debug. Each approach comes with trade-offs. Brute force, for instance, is simple to implement but computationally expensive for large inputs. Backtracking with pruning is generally the best choice for most scenarios, but it requires careful handling of constraints like visited markers. Dynamic programming is useful when the goal is counting permutations rather than generating them explicitly, but it's not ideal for this specific problem in its standard form. Understanding these trade-offs will help you choose the right approach for the problem and the context in which you're solving it. Great job! We've summarized the key points of the solution to problem number 1079, letter tile possibilities. Remember, recursive backtracking is a powerful tool for solving permutation and combination problems. Practice similar problems to strengthen your understanding. Don't forget to like and subscribe for more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!